All right, here we go. Unit 4, Lesson 3, Related Rates. This is one of my favorite topics in calculus. We're going to be able to use some of the stuff we've been doing with implicit differentiation. We're going to be able to give it a real-world context in comparing different items that are changing relative to each other. So like inflating a balloon or water leaking out of a tank. Times when you can have two items that are both changing with respect to time. And so that's going to be the whole idea today is everything's changing with respect to time. No better way to do this than just to jump into it. So here we go. Air is leaking out of an inflated balloon in the shape of a sphere. Big key to these types of problems. Draw yourself a little picture. Take 10 seconds, draw yourself a little picture to make sure you understand what's going on. We've got a balloon in the shape of a sphere, more or less, and air is leaking out of that balloon. Specifically, air is leaking out at a rate of 230 cubic centimeters, centimeters cubed per minute. I'm going to show you right now how I would start to annotate these in the language of calculus. Air, right? Think through quantities. It's not a length. You don't have centimeters of air. It's not area. You don't have centimeters squared of air. It's actually a volume. And so the way we're going to annotate this is we're going to say the derivative of volume with respect to time equals negative 230. Right? So all I'm saying there is for an infinitesimally small change in time, right? The instantaneous change in time, volume is changing by 230 centimeters cubed. That's what dV/dt means. It means how much does volume change for a tiny change in time. At the instant when the radius is 4 centimeters, so I'm going to draw this in my picture here. When the radius is 4 centimeters, what is the rate of change of the radius? So basically, if you know how fast air is leaking out at a rate of minus 230 centimeters cubed, and you know how big the balloon is, how fast is that balloon shrinking? How fast is the radius of the balloon shrinking? And so variables we have in the problem, right? If we are thinking about, the variables that are involved, we know the radius of the balloon is important. All right, so the radius of the balloon we actually know is 4, at least when we are interested in the problem. We know the volume is changing. The volume is changing at a rate of negative 230 centimeters cubed. And finally, we want to know how fast is the radius changing? How fast is the radius changing? Identify which of any of the variables remain constant in this equation. So this one, there's none that remain constant, right? If the balloon is shrinking, all of these things are changing. We'll see an example of a constant variable in a second. So that's good. Okay, the rates that are given and the rates that you wish to find. So, right, the radius was given. The volume change was given. And dr/dt is what I'm going to label as the need. We need to find the rate of change of the radius of the balloon at that instant in time. And so the key to these problems is you need to come up with, right, from your own brain, from your own knowledge of geometry and algebra 2, a formula that links all of these variables, right? A formula that links all of these variables, in this case, radius and volume. And so you can look these things up, right? But one thing you want to remember here is that the volume of a sphere is equal to 4/3 times pi times the radius cubed. This is just the formula for the volume of a sphere. And remember, what we want to know is what is the rate of change of the radius with respect to time. So what we are going to do is we are going to differentiate both of these sides. We're going to take the derivative with respect to time, and we're going to take the derivative with respect to time, and this is going to require our remembering of implicit differentiation. And so we go to take the derivative of volume. Well, the derivative of v with respect to v is 1, but then the implicit differentiation chain rule tells us that this will have to be tacked on with a dv dt. Another way to think about this is if you just apply the derivative operator with respect to time to a single variable, it's just dv dt. It's how fast is volume changing with respect to time. And that's going to be equal to, right? That's going to, I guess I'm skipping a box here so that we get to move this all the way down. So we're going to have dv dt, and that's going to be equal to 4/3, right? That's a constant. Pi is a constant. R cubed is a variable. So that is going to need its derivative taken. And so remember, when we take the derivative with respect to time of r cubed, what we have there is 3r squared dr dt. And so this is going to be equal to 4/3 pi times 3r squared dr dt. And so those 3's will cancel, and you'll just be left with this is equal to 4 pi r squared dr dt. And so that's what dv dt is equal to. Now, if we look back at our original picture, right, things we had labeled, dv dt, we know the volume is changing. The volume is leaking out at negative 230. I think I actually wrote this wrong the first time. I forgot that pi. 230 pi cubic centimeters per minute, so minus 230 pi. And that's going to be equal to 4 pi. The radius we also labeled. In the beginning of the problem, we were asked when the radius is 4, what is this rate of change? And then finally, dr dt, we do not know, right? And that's the whole idea here, is that we're trying to figure out the thing that we do not know. And so now we just have algebra 1 because everything's been solved for. 230 pi is equal to 4 times 16. This is going to be 64 pi dr dt. Negative 230 pi over 64 pi. So whatever negative 230 divided by 64 is, that is going to be the rate of change of the radius with respect to time. And so to recap, if we know how fast the air is leaking out of the balloon, we can now say how fast its radius is shrinking given a given start point of a radius. So that's pretty cool. So now we can start to relate these concepts from the physical world. So let's just do a couple more here. A stone is dropped into a calm body of water, causing ripples in the form of concentric circles. So what that means is, right, you throw this stone, the stone lands in the water, and what happens is it causes our normal ripples to happen in the water. The radius of the outer ripple, so all we care about is this outer ripple here, the radius is increasing at a rate, okay, increasing at a rate. So what we're talking about is dr dt equals 1 foot per second, right? It's a speed, 1 foot per second. When the radius is 4 feet, and so I'm going to start to just like skip a bunch of these steps here. When the radius is 4 feet, so that's what we care about, at what rate is the total area of the disturbed water changing? So at what rate is, I'm going to fill this in now, what rate is the area of the circle enclosed by that outer ring increasing? And so we can pretty much we can skip to these part 4 here. Write an equation that links all of these things. Well, it's the area of a circle. If I know the area of a circle is equal to pi times the radius squared, as long as I differentiate with respect to time, I'll be able to plug in the radius and I'll be able to plug in the speed of change of the radius and find how fast the area is changing, because we want to know at what rate is the total area of the disturbed water changing. And so here we go. We differentiate with respect to time. So the derivative of area with respect to time, we just leave as the derivative of area with respect to time, is equal to pi is a constant, don't forget that, but r squared is a variable that's going to take the chain rule. So we're going to have pi times the derivative of r with respect to r is 2r. Chain rule, r is a function of time, so we need the derivative of r, the radius, with respect to time. So here's the trick. dA dt is what we wanted to know. The radius, we do know. We know is 4. So we have pi times 2 times the radius of 4. The whole key here is, as long as you know one of these, either how fast the area is changing or how fast the radius is changing, you can figure this out. The radius is changing at a rate of 1 foot per second. So the derivative of the area with respect to time, which is what the question asked for, is equal to 8 pi. That's all. 8 pi, and if you want units there, right, you just got to think about what is the units of area. Well, area is feet squared, because area is always squared, over seconds. So 8 pi feet squared per second. Last two more quick examples here. Just wanted you to see one more with rectangles. The length of a rectangle is decreasing at a rate of 2 centimeters per second. So I'll just immediately write that. dl dt is equal to negative 2 centimeters a second, while the width is increasing at a rate of 2 centimeters per second. dw dt is equal to 2 centimeters per second. When L is 12 and W is 5, when L is 12 and W is 5, find the rates of change for each of the indicated quantities. Okay, so here we go. Draw a picture, right? Area is equal to length times width. And so we have area is equal to length times width. First things first, I'm going to take the derivative with respect to time of both sides. So we're going to do our derivative operators here. We're going to have the derivative of area with respect to time is equal to, this is tricky. There are two variables here being multiplied. We need the product rule so that we have the derivative of L with respect to time. That's your F prime times G. So that's dL dt times just the straight up width plus the length times dW dt. So product rule, F prime G plus F G prime. And so we have almost all of these things. The length is 12, the width is 5, and we know dL dt and dW dt. So we can just straight up plug these in. dA dt is equal to, dL dt we're told is negative 2, the width we're told is 5, plus the length we're told is 12, and dW dt we are told is 2. And so we'd have the areas changing, negative 10 plus 24 at 14 centimeters squared per second, because that's how area is measured, centimeters squared per second. The perimeter, right? So again, the whole idea here is you just need to come up with these equations on your own. That's the toughest part. Once you see this, the rest of this is really easy. Take the derivative with respect to time. The derivative of the perimeter is equal to 2 times the derivative of the length with respect to time plus 2 times the derivative of the width with respect to time is equal to 2 times negative 2 plus 2 times 2 equals 0. That should make sense. If the length and width are changing at opposite rates, well, then the perimeter is not going to be changing at all. The perimeter is not changing if your length and width are changing at opposite rates. But your area might be, right? The reason for that is, remember, things that are like this are really inefficient in terms of area. So the closer you get to a square, the more you're maximizing your fencing. And so in this example, right, the length is the longer one, the width is the shorter one, so it makes sense if the width is increasing and the length is decreasing, but your total amount of fencing staying the same, your area is getting bigger, 14 centimeters per second, even though your perimeter is not. So you're adding area without changing the perimeter, and so you're getting more efficient. All right, last one here. This one just to really mess with your heads. The length of the diagonal of the rectangle. So how fast is this diagonal changing? And this is just a common one that comes up, is that you need to use the Pythagorean theorem. The length squared plus the width squared is equal to, we'll just call it c squared. And so we take these derivatives with respect to time, 2L dl dt plus 2W dw dt is equal to 2C dc dt. And I love this problem because you start to see what happens at the very end. 2 times, remember we're told the length is 12 and the width is equal to 5. 2 times 12 times dl dt, you'll remember, is negative 2, plus 2 times the width is 5, dw dt, we're told is, remember, is positive 2, is equal to 2 times, what's c? C, remember, is the diagonal of this rectangle. We weren't given c, but that's okay because we can find it. Remember, 5 squared plus 12 squared is equal to c squared just by the Pythagorean theorem. So 25 plus 144 is equal to c squared. 169 is equal to c squared. C is equal to 13. So c is 13. dc dt we don't know, right? Because we were trying to find how fast the diagonal of the rectangle was changing. And so overall here, we can do this all out. This is going to be negative 48 plus 20 is equal to 26 dc dt. And so you get here negative 28 is equal to 26 dc dt. And so finally, dc dt is equal to negative 28 over 26, or negative 14 over 13 if you divide those both by 2.